So that is what we are trying to do. Now equate the equations A and B, which is the mass evaporation rate is nothing but, so from the heat transfer 4 pi Rs lambda by Cpg natural logarithm of 1 plus Bt, here 4 pi Rs rho df A into natural logarithm 1 plus By. When you equate this, you can see that there is no assumption made till now, and the main assumption made is the properties are constant. We have not made any other assumption like Lewis number 1 or anything here till now. Okay. So now when you equate this, you can see that the 4 pi Rs cancels, and we can write, so bring this to the left hand side. So lambda by Cpg, so here Cpg rho dfa. Okay. So this parameter go take to the left side, that this is actually equal to the Lewis number. Okay. So we can write this equation as 1 plus By will be equal to 1 plus Bt power the Lewis number, which is nothing but lambda by Cpg rho into dfa. That is the number. So if you assume Lewis number equal to 1, okay, if Lewis number is equal to 1, we can say Bt will be equal to By, but we have not made assumption itself. So without making that assumption, we are saying that individually the properties are constant. Okay, when the properties are individually taken as constant, that means that they can be evaluated from average temperatures, but we have not made the assumption that Lewis number is 1. So this assumption has not been made. So this appears here in this term. We can see that when you want to compare the transfer numbers, we have to compare this like this: 1 plus By is equal to 1 plus Bt power whole power Lewis number. So we can calculate the Lewis number, may not be 1. See, for when it will be 1, if the molecular weight of the fuel is almost same as that of the ambient fluid. There are only binary fluids here. If that is the case, then Lewis number will be close to 1. Okay, or else it will not be 1. So that assumption has not been made. We can keep this and try to work out. So use this equation. You know what is By? By is Yf S minus Yf infinity divided by 1 minus Yf S, and Bt you know Cpg T infinity minus Ts divided by Hfg. So when you substitute this, you can find Yfs as a function of Ts, or other way also. Okay. So that is what we are going to do this. So using this, mass fraction of the fuel at the interface can be written like this. So Yfs is written in terms of a Ts here. So Yfs equal to 1 minus Yf infinity divided by 1 plus Bt, correct, power Le. So that is what we are trying to do. So you can calculate Lewis number based upon the properties. So now if you want to get the value of Ts, you can also write that this equation in keeping Ts as unknown. So this is the equation C, which actually couples the heat and mass transfer. So that is what we want. So once you know what will be the equilibrium temperature, so you know the value of T infinity, you know the value of Cpg, Lewis number, then Hfg, and this you can take very close to 0. So this you can even neglect it. Okay, so that take it to 0, Yf infinity. So Ts is an unknown here. So what we can do is, what is the equilibrium temperature for a given T infinity? There is a particular temperature which will be Ts, and that will obey this equation. Do you understand? So when you try to equate these two, there is a particular temperature Ts which will give a value of the mole fraction. See, for example, Ts, you get the saturation pressure at this Ts, from this Ts. Okay. So once you know the Ts value, you can get the saturation pressure at the Ts. So this is will give you the mole fraction of fuel, which is saturation pressure at Ts divided by P. Okay, total pressure P. Okay. Now mole fraction will lead us to mass fraction, and once mass fraction is known, you get this value. So we can, that is the only particular value of Yfs when you have a particular Ts. So that will obey this equation. So that is what the equation is. So, this equation C is very important, and that illustrates that the balance between the heat and mass transfer, and that will allow us to calculate the equilibrium surface temperature and the corresponding fuel mass fraction at the interface. Okay, now you can see that if T infinity tends to infinity, so T infinity tends to infinity, very large value. So, what happens here then? This denominator will be 0 here. So, YFS will tend to 1. Now, if you take H of G tending to 0, that will happen at critical condition, correct? So, when the pressures are high and you reach the critical temperature and critical pressure conditions, then H of G tends to 0. So, we know this. So, you take any phase diagram, okay. So, this is the critical point, okay, where the H of G is 0. So, all other points you can see based on your pressure, say P1, etc., you have these regimes here. So, this is P2 and so on, and this is the critical isobar PC. You will see that is a critical point. So, the corresponding temperature being Tc, where H of G equal to 0. So, now in these regimes where the pressures are lower than the critical pressures, etc., there is a definite saturation temperature, say T sat 1, etc. Okay. Now, here if this is say corresponding H, this is the vapor state. So, this is Hg and this is liquid, so this is HF, then there is a difference in this. So, H of G will be equal to Hg minus Hf. Now, at the critical point you will see that Hf equal to Hg, that means Hfg tends to 0. When you reach the critical point and Hfg tends to 0, then this 1 plus this will be infinity. So, this denominator will be infinity. So, again Yf will tend to 1. So, Yfs tends to 1 under two conditions, T infinity tending to infinity or Hfg tending to 0. So, we do not go to the critical point. So, when you are in the equilibrium regime, there should be a definite value of Hfg, positive value of Hfg should be prevail. So, that is very important thing. So, this is first thing you get from this relationship. Second one is, since the mass fraction of the fuel vapor at the droplet surface is a function of Ts, okay, correct? Yfs is a function of Ts. The values of this may be evaluated by solving the equation C, and we need one more equation that will relate the Yfs and Ts. Okay. So, that is called thermodynamic relation, which will relate, see that is what I have written here. Once you know the value of Ts, or at least guess the value of Ts, you will be able to find the saturation pressure P sat at that value of Ts. So, that relationship is called the thermodynamic relation, which is one of them is the, there are several relations. One of them which is actually applicable for ideal gases is Clapeyron equation. Clapeyron equation, we will actually do one more one problem, worked example with this. So, now this is the Clapeyron equation, in which you can see that the mole fraction of the fuel at the interface is nothing but the saturation pressure by the total pressure, that is the pressure ratio, okay, partial pressure equal to exponent of the latent heat of vaporization of the fuel divided by the specific gas constant. So, this is nothing but Ru divided by the molecular weight of the fuel, okay, specific gas constant of the fuel into 1 by T, any temperature. So, this P sat at any temperature T I am going to get, okay, that T unknown as a known temperature, but I will get the value of P sat. Now, boiling point of the fuel also is there. So, we see that if temperature T equal to T boiling point, what happens? This is 0. So, this will be 1, that means X of S will be equal to 1. So, as T, this is surface temperature, say this is surface temperature, and this, when surface temperature is increased very close to boiling point, tends to boiling point, okay, as I told you it may not reach the boiling point. So, it tends to boiling point, then X of S tends to 1. So, this is the Clapeyron equation, thermodynamic equation relationship, which connects the saturation pressure and temperature, unique relationship between the saturation pressure and the temperature. So, that is the equation. So, this and this, if you use this C and this D, if you use, you can get the values of the YFS and TS. Okay. The procedure for calculating the equilibrium temperature is as follows. So, you fix the ambient temperature at any given ambient temperature we can do this. So, let us do this. First you assume the value, you do not know the value of Ts. So, let us say see if you take any fuel, for example say NF10, the boiling point of this will be say 371 Kelvin boiling point. So, now I can assume Ts at the surface can be say 360 Kelvin. So, assumption, this is assumption made, because I know that it will never reach the boiling point. So, this is boiling point of NF10 is 371 Kelvin. So, this Ts will be close to boiling point based upon the ambient temperature. See, for example, now ambient temperature T infinity is say only 350 Kelvin. So, now there are scenarios, you have to understand this gas is very important. So, let us take, so there are 3 temperatures I have, so T infinity, T boil and T surface, correct. So, now out of the 3 temperatures, this 350 Kelvin I will put for this, and my boiling point is 370 in Kelvin, okay. Then the surface temperature cannot exceed this T infinity, okay. So, surface temperature can be guessed as say 340. So, definitely it should be less than the T infinity, that condition we have to understand. So, Ts will be less than the T infinity. Evaporation, please understand, in the evaporation scenario, okay, I fix the T infinity. Now, T infinity fixed actually less than the boiling point. Boiling point is 370 and 350 is the ambient temperature I am fixing. So, evaporation will take place, but the surface temperature will not exceed the boiling point. So, it will not be even go close to that, because it is actually less, ambient temperature itself is less than the boiling point. So, now if I say a scenario where the T infinity is taken as 400 Kelvin, which is actually greater than 370, which is the boiling point, then I may reach the temperature close to boiling, I cannot exceed boiling point. Please understand, I may go to 360 here. So, please understand that Ts can be either less than the ambient temperature T infinity if the T infinity itself is less than the boiling point, or it may be less than the boiling point if the ambient temperature is more than the boiling point. So, this is the important thing you should remember to guess the value of or assume the value of Ts. So, if the situation is 350 for T infinity, I cannot guess Ts as 360, because I cannot say that the boiling point is 370, I am taking a temperature less than that, that is not possible. So, either seeing the scenario, if T infinity itself is less than boiling point, you have to take a temperature of the surface which should be, it will be actually less than the T infinity, which is less than the boiling point, or otherwise if T infinity exceeds the boiling point, then my surface temperature cannot exceed the boiling point, so it should be less than the boiling point. Okay, so that is it. So, you cannot say that now ambient temperature is more, so the droplet surface temperature can exceed that boiling point to reach that, it is not possible. So, that keep in mind that, okay, these two situations, and first value of Ts is assumed based upon this, then use the equation D, that is the classical equation here. Classical equation is equation D, thermodynamic relationship, and find the saturation pressure Psat at this Ts. Okay. Now, Psat is known, so find the mole fraction. So, once you know, equation D is used again. So, Psat is calculated, or XFS is calculated straight away, the mole fraction of the fuel. So, now you know the mole fraction. So, XFS is calculated as Psat by P at Ts by P. So, now you know this. So, what is the molecular weight of the mixture? Molecular weight at the interface will be equal to XFS into molecular weight of the fuel plus 1 minus XFS into molecular weight of the ambient gas A. Okay, now you know this. Now find YFS. Okay, molecular weight of the mixture is known, and find YFS. So, that is what I have told, that mole and mass fractions of the fuel at the droplet surface are calculated. So, straight away the Clausius-Clapeyron equation will give you the mole fraction, calculate the molecular weight of the mixture and calculate the mass fraction. So that is done. Okay, now you know the mole mass fraction of the fuel. Go back, calculate the values here. So this Bt and By can calculate and use this equation and see whether this equation is satisfied, correct. So calculate the values of Bt and By and see whether equation C is satisfied or not, because we have guessed the value of Ts, that will give you a value of YFS, but if you calculate YFS using equation C, that may not be the correct value what you get here. So this may not satisfy. So that is a unique combination of Ts and YFS which will satisfy the equation C. So that is not going to be there here. So you will not get the value here. If you don't get this, then your assumption of Ts is not correct. Now what you do is the Ts value is adjusted or iterated and the steps 2 to 5 are repeated to get the convergence of equation C. That is, equation C will be finally satisfied. So whether you are see, let us say for Epton itself, the second case let us take T infinity is 400 degrees 400 Kelvin and T boiling point is 370 Kelvin. Now your Ts can be say 360 Kelvin. I am just giving some idea, 360 or so. As ambient temperature increases, your Ts will increase. So this is iterative procedure to calculate the value of Ts and corresponding YFS values. So that is the equilibrium condition at which, so once you get the Ts and YFS value, then you calculate the using any equation like for example this, any one of this you can use to calculate the mass evaporation rate. So accurate value of see Bt, if you want to calculate the Bt, you will have to know the value of say Cpg T infinity minus Ts. So Ts value should be known to you, calculate Bt. If you calculate By, you know this value, again YFS is required for this. So once you calculate the correct equilibrium values of Ts and YFS, you can get the mass evaporation rate using one of these equations. Okay. So this is what the procedure which is used to calculate the interface quantities, that you have to guess the value of Ts, and if I understand that, I will repeat once again, when the ambient temperature is less than the boiling point, your Ts should be less than the ambient temperature. When the ambient temperature is more than the boiling point, your Ts should be less than the boiling point. So it cannot exceed the boiling point. Okay, now again this is the curve what we have basically. See, I can do this exercise for several ambient temperatures T infinity. So you can see that the equilibrium temperature Ts for various ambient temperature is shown in this graph. Okay, so these lines, so this is a T infinity 1, this is T infinity 2 and so on. So several T infinity values I get and plot this. Okay, now what is this curve? This curve is nothing but the equation C, which is this equation. So equation C. So when I try to calculate YFS as a function of Ts etc., you get this equation. So this is this YFS as a function of Ts, I plot this. So various I will vary the Ts and try to get this curve YFS, I will try to get the values of this. Okay. Now this dark line represents the equation D, thick black line. This is the Clapeyron equation. Okay, now what are the equilibrium temperatures? These intersections are the equilibrium temperatures. Graphically, correct? These are the equilibrium temperatures. So you can see that the equilibrium temperature Ts values, these are Ts. So this is a corresponding to, so for example this is T infinity 1. So now this will be the corresponding Ts1. So Ts1 corresponding value for this Ts1 is the equilibrium value for the T infinity 1. Then similarly T infinity 2 corresponding Ts2 and so on. So this will be the corresponding equilibrium of the intersection of these curves with this Clapeyron equation will be the Ts. So now you can see that as T infinity increases, the Ts also increases. Okay, but please understand that it cannot exceed the boiling point. Okay, if the scenario is if T, so in all these cases you have to understand one thing, the boiling point is here, so always I have considered the temperatures basically you can see that always the Ts is less than the boiling point. Okay. T infinity itself can be less than boiling point in some scenario. If that is the case, then the Ts cannot exceed T infinity itself. So that is there are two things which you have to understand in this. So the graphically I am trying to show you the procedure. What you do, I have illustrated here. Like assuming a value of Ts, you calculate the Clapeyron equation, calculate the Psat and find the mole and mass fractions, then calculate the transfer numbers, then use the equation, verify the validity of equation C. If not, adjust the value of Ts and iterate. So graphically, equation C are several based upon the T infinity value, fixed T infinity value, you get curves for equation C, and those curves should intersect the equation D, which is the Clapeyron equation. Corresponding to that in intersection for a given T infinity, we will get the value of Ts. Okay. This is about the evaporation, where you try to find the equilibrium values of the surface quantities like Ts and y of infinity. Once you get that, you will get the equilibrium evaporation rate or steady or equilibrium evaporation rate. M dot. So let us move on to droplet combustion. So just okay. So let us move on to droplet combustion. So again, we will assume the problem to be spherically symmetric. So that means the droplet is spherical. And a flame surrounds the droplet. Okay. So what happens if you just ignite the droplet which is evaporating, then a diffusion flame is established around the droplet. So there is a flame which is established around the droplet, and this is the flame. So this is diffusion flame. Okay. Now you can see that this is also a spherical. I will say spherical again here. So droplet is spherical. The flame which is surrounding the droplet is also spherical. The radius of the droplet at any time instant is say Rs, and the flame surrounds the droplet and its radius is say Rf. So the ignition source on an evaporating droplet will create a flame over the droplet, and the flame sustains at the radius Rf. Okay. So this is the scenario at a given time instant. So what happens is fuel from this droplet surface goes to the flame, this fuel, and ambient air, from the ambient the air comes to the, or the oxidizer comes to this, and products are formed here. So that is what the diffusion flame nature is here. So you can see this when this burns, it reduces the droplet diameter. So what happens is the same type of this. So if you say d square for this time in this coordinate, spherical coordinate, and if it is a steady burning, okay, a steady burning or steady droplet combustion, say steady burning problem, you can see that there will be a constant rate. The rate at which this burns is a constant. So the whatever assumptions what we have made for the evaporation will be there. We can also make few more assumptions here. So when you talk about the structure of this flame, okay, any flame you will talk about structure, it is like this. So you can see this is the droplet surface Rs and the flame radius Rf. Please understand that this is a very thin flame basically, but I have given a finite thickness here. In practice there will be some finite thickness. So I have exaggerated and shown the thickness here. So what happens is you can see that the fuel from this mass fraction of the surface YFS goes and consumed, it is fully consumed at the flame zone. Similarly, oxygen from the ambient is consumed to the flame zone like this. So fuel and oxygen are consumed. Where the fuel and oxygen are consumed, you can see that the product has the maximum mass fraction there, and the product actually diffuses in this zone. This is called a zone between the flame and the surface. So, this zone I call as inner zone between the flame and the surface of the droplet. The outer zone is obviously the ambient, from the flame to the ambient, it is called outer zone. The product also is transported to the ambient. So, the product which is formed at the flame zone maximum value is diffused towards the inner zone and transported towards the outer zone. Okay. So, oxygen is actually transported towards this zone, and you can see that the oxygen cannot penetrate the inner zone, fuel cannot go to the outer zone because it is consumed within the flame zone. Temperature also is maximum because the reaction is completed in the flame, and you can see the temperature decreases towards the what is called Ts, surface temperature. Again, please understand, a steady evaporation, like in steady evaporation problem, the steady combustion problem, there is a definite value of Ts and YFS, equilibrium values. So, again we can say that the equilibrium prevails. So, we will make the assumptions more clear in the next slides. So, now once the temperature is maximum here, it actually decreases towards the surface to reach the equilibrium temperature Ts, and towards the ambient it again decreases to reach the ambient temperature T infinity at a far off radius. So, this is the structure of the droplet flame and then the radial structure profiles. Okay. So, fuel from the droplet surface or RS basically reaches the flame zone by both convection and diffusion by Fick's law. We have seen that. So, this is like actually the flame actually separates the part. For example, the ambient temperature will not have any influence now. In the previous case, evaporation case, only the ambient temperature actually was the driving force, correct, for evaporation. In this case, the flame itself is there, which has higher temperature. So, now you can see that the surface temperature can be larger than the ambient temperature. In the previous case, what we told was the surface temperature cannot be larger than the ambient temperature. Then if the ambient temperature is less than the boiling point, then the surface temperature cannot exceed the ambient temperature. If the ambient temperature is more than the boiling point, then the surface temperature cannot exceed the boiling point. So, in this scenario, you can see that there is no influence of the ambient temperature because of a high temperature. This is the flame temperature Tf. That high temperature zone is there in between the droplet surface and the ambient. Okay. Similarly, the oxygen from the ambient is transported towards the flame and it is consumed completely in the flame zone. So, this is the typical structure. Now, like in any diffusion flame, the transport processes are going to control the combustion zone, correct? How fast the fuel is diffused, how fast the ambient air comes to the flame zone, etc., will control the flame zone location, etc. But if you see, in this case, additionally the evaporation process also is there, like the rate at which there is a heat and mass transfer occurring to the droplet surface, that also will be. So, this is heterogeneous in nature because this has to cause a phase change basically, and this process is slower. These processes are much slower than the chemical kinetics. So, that means that I do not need chemical kinetics at all to analyze a droplet combustion problem, especially when it is surrounded by a diffusion flame like this. So, this problem can be analyzed by considering only the transport process in mass and energy conservation equations as done in the simple chemical reacting system SCRS. We already discussed that. So, we need not invoke any chemical kinetics here. So, that is one of the things. Then we will just some characteristics we will see. When a flame surrounds the droplet, this scenario is similar to droplet evaporating in a high ambient temperature environment. Okay. So, if you go back,